you might see problems where you have a bunch of masses tied to strings, and it might say it's static, right? So nothing is moving, and it might say find the tension everywhere. Everywhere. All right, so let's think. Tension is a property of a string. It's actually not a force vector, it's a scalar property, but remember the tension has the unit and magnitude of the force that's applied to an object that it's tied to. Okay, so that's tension, and they want to know the tension here, and I guess the tension there as well. You may also remember the tension had this property that it's the same everywhere, but that's only for a continuous string where nothing is applying a force along the string. You know, in this case we have multiple strings, so it may not be constant everywhere. So all that said, let's look at it. Let's find T1 and T2 and T3. All right. So the way to find it in a static situation is you just pick the right mass or system of masses and you do a free body diagram and you apply Newton's second law with the force, the sum of the forces equal to 0. So to get T1, the easy one is just this. Is just say sum of the forces equals 0 for this mass only. Right, so the forces on this mass, we have mg down and we have T1 up. All right, so if we consider up the positive direction, then we have T1 minus mg equals 0. The first tension, sure enough, is just mg. Not bad. Now we need tension 2. So we could do it by just looking at this mass. One way to go. And we're going to say the sum of the forces on that mass is 0. Let's free body diagram it. And it's got mg pulling down, but it's also got T1 pulling down. Right? If you imagine it just sitting there, two things pulling it down and T2 pulling it up. So sum of the forces T2 minus T1 minus mg equals 0. Of course, we know that's mg. So it's just that T2 is 2mg. So you don't look at this and say, oh, it's a continuous string, the tension is constant. Right, here the tension is mg, and since these are the same mass, this one is 2mg. And I actually set up the demo so I could show you this to you. There's a way we can measure the tension because the sound that you hear when you pluck a string, the frequency of the sound is proportional to the square root of the tension. So what we can do to show you that this is pretty much the same situation. Here we have a mass and a string, the equivalent mass and the string going up and being tied off. So if I pluck it here, you can listen real close, and let's hear this pluck here. So think about that sound, and now I'll pluck it up here and listen real close. So you can see how it was higher. It was higher because the tension is higher, and the frequency goes as the tension. T3 you could try to solve. Really, then you can apply the rules for strings because a pulley does not apply any force along the length of the string. Right? It applies a normal force so that the string doesn't fall. It holds the string up, but along the string direction it applies no force. So you can just say the tension is constant around the pulley. So then you can say T3 equals T2 in this case. Now that's not always going to be true. This is for an ideal massless, frictionless pulley, which really doesn't exist. If you consider the rotation of the pulley, something like that, if you have a dynamic situation, you can have the tension change across the pulley. But in this case, it's the same thing. So T3 is T through 2 is 2mg. And we could even check it. I could reach up here. We have a small region of T3 up here. Oh, that was way too high. Oh, what's going on? What's going on is the length is shorter. In addition to the square root of t, it goes as 1 over the L, 1 over the length. So I set these lengths about the same, but that length is so short, it takes the frequency way up. So we can't really rely on that. The tension here and here are actually constant, or equal.